It's a great pleasure for me to introduce this year's Terzaghi Lecture. It's instituted by the ASCE Board of Direction in 1960. The Terzaghi Lecture was established by what's now the Geo-Institute in honor of Karl Terzaghi. Annually, the Geo-Institute Board of Governors recommends a distinguished engineer to deliver the Terzaghi Lecture. And this year's Terzaghi Lecturer is Professor Carlos Santamarina. J. Carlos Santamarina received his undergraduate degree in civil engineering from the National University of Cordoba in Argentina. He then obtained a MS in civil engineering from the University of Maryland and a PhD in civil engineering from Purdue University, finishing there in 1987. He joined the faculty at Polytechnic University in Brooklyn and in a few years moved to University of Waterloo in Ontario, Canada. In 1996, he moved to the Georgia Institute of Technology here in Atlanta, where he currently holds the Gozueta Foundation Faculty Chair. Professor Santamarina's research interests are diverse and multidisciplinary, ranging from the fundamental understanding of particulate media, characterization of geomaterials, and more recently, geotechnology as it relates to our energy needs and sustainability. He's made significant contributions to our understanding of fabric formation and evolution, cementation and stiffness, damping, filters, and clogging, as well as advanced materials characterization methods. By any measure, he's extremely productive, having written multiple textbooks, more than 200 journal papers, and has guided at least 35 PhD students. I suspect that number is a little low by now. And he shows no signs of slowing down, I can assure you. His breadth of interest is reflected in his publication list, which by my quick count includes papers in 39 different journals. The list includes all the geoprofessional journals that you'd recognize, as well as a few titles like Applied Physics Letters, Journal of Approximate Reasoning, and the Journal of Man-Machine Studies. And speaking of publications, I was in a Professor Santamarina lecture, it was many years ago now, and he had been traveling and doing work on the plane like many of us do. And he was making a point how it's nice to sometimes take a break from all of the technical literature. And I'm thinking, wow, he's gonna come clean. He reads People magazine on the plane, but no, his guilty pleasure was Scientific American magazine. Professor Santamarina is a frequent keynote speaker at international events. He was the British Geotechnical Association Touring Lecturer in 2012, to name a recent one. And he's a past winner of the ASTM Hogan-Togler Award. He's a member of both Argentinian national academies, that's the Academy of Sciences and the Academy of Engineering, and he's a recipient of numerous other awards and distinctions. And in putting together this introduction, I spoke to many of his colleagues, and there was a common theme in all the response I got from talking to them, and that is his exceptional curiosity, enthusiasm, and generosity. He's always interested in what you're working on, and he's always willing to share his valuable experience and insightful responses to your questions. So, Professor Santamarina, would you please join me at the podium?
Well, Billy, thank you for your kind and generous and personalized presentation, introduction. Colleagues, it is indeed a great privilege to be here with all of you, sharing this annual tradition when we get together, not only to look at the past, at our history, but also to imagine and to dream the future. In so doing, I have two very simple goals today. The first one is to show you some data that will make it clear that the energy challenge is critical and it is here, and that we geotechnical engineers have a central role to play in developing a sustainable energy solution to the world. The second one is to see some of the implications of embracing this challenge. The manuscript that I'm trying to finish for this, to document these studies, is going to be quite extensive. Now, for the sake of this presentation, I will only look at the essence of soils and sediments. That means we're going to look at the grains, and we're going to look at the fluids. And then we will try to explore some of the evolving engineering problems that are not so well understood or explained yet. When we look at our past, we see that our field has been driven to address multiple needs that have changed through time. One of them, at the beginning of the 20th century, was the infrastructure. Then we had to build the dams. Earthquakes in the 60s particularly triggered much research and development. And then the environmental challenges in the 80s had tremendous implications. We even had to change the name of many of our programs and our journal. At the same time, we either developed technology or we adopted technology that was in progress in other fields. That is the case for laboratory and field exploration, geophysical methods. Without them, we wouldn't have petroleum today. And the advance of computers and methods had a tremendous impact that is still manifesting in our field through numerical methods. Now, whenever we were challenged by these new needs, we looked back into the foundations of knowledge. We went back to the sciences. We re-explored the mechanics, the physics, the chemistry, and more recently, the biology. Today, I would like to do the same as we explore the energy challenge. Why energy? Well, because whenever we seek the ultimate goal, which is to have a pleasant life with great quality of life, we see that it is basically controlled by the availability of energy. It is so much so that if we plot most quality of life indicators, they exhibit a great correlation with power consumption, that being life expectancy, infant mortality, ability to receive an education. Some of these parameters can be combined to make it even more predictive of future energy needs. And in this case, there is some combination here of those parameters into an index that we call quality of life. We see the very strong correlation with power consumption. Furthermore, we can track these numbers for the last 2 or 3 decades, and we see that there is a very clear trend. All countries are improving quality of life. That is the good news. But we're all doing it at the expense of consuming more energy to a point that this may become unsustainable. Today, we consume 17 terawatts. That is a huge number. And in the next 25 years, we are going to have a demand for 50% higher energy consumption. Let me put this in perspective. That would be approximately 10,000 nuclear power plants of the largest ones we've ever built, and we have only built about 500 in the last 60 years. This is the amount of additional energy that we will have to produce to sustain current growth. So I think that as geotechnical engineers, we have to think very seriously, what can we do to contribute to the development of a sustainable energy solution whereby the developing world can increase quality of life with minor increases in energy consumption, while the developed world can decrease power consumption while still improving quality of life. In order to understand some of these problems, it is good to go back to see what are our energy sources and what is the origin of those resources. Let's focus on one of them, which are fossil fuels. 85% of our energy or more worldwide is based on fossil fuels. That means coal, gas, and petroleum. And you may wonder, how did those form? Well, let's look at the history of the Earth as geotechnical engineers. The Earth is approximately 4.5 billion years old. At the beginning, it was abiotic, and life appeared approximately 3.5 billion years ago. During that early stage, the atmosphere was basically a heavy CO2 atmosphere, but microorganisms fed with energy from the sun began capturing the CO2, converting it into organic mass, organic carbon, and releasing oxygen, and that had a tremendous effect changing the atmosphere. In fact, many of our minerals today are oxides and the carbonates, both of them the result of the effect of these microorganisms. Eventually, organic matter began accumulating, and just to make the round numbers here, it took approximately 1 billion years to accumulate this organic matter in what would mature eventually to become coal, petroleum, and gas. Let me expand this scale by 2 million times, and let's look at the last 10,000 years. And all of a sudden, that little yellow line that was at the top now is expanded. That Gaussian-looking curve is the history of fossil fuels on the Earth. It started approximately 150 years ago with the Industrial Revolution, and it will extend probably another 200 years when reserves, as we know them today, will be completed, will be exhausted. So the history of fossil fuels is only 300 years long, and it took 1 billion years to form. So there is not only a contrast here in time scales, let's look at some geometric scales. This is the Earth, as you can see in Google Earth. However, that cloud that is around it, which appears to be the atmosphere, is in fact exaggerated. The atmosphere is only 10,000 meters, 10 kilometers thick. For those of you who are closer to the screen, you may see now a very thin shell superimposed on the image. That thin line is in fact thicker than the atmosphere. And that very thin shell is responsible for controlling climate, all the energy balance of the Earth, and we are burning fossil fuels, producing CO2, emitting them into the atmosphere, and accumulating them in that thin layer, and there is great concern for climate change associated to that. Therefore, many people are exploring the possibility of capturing the CO2 before we actually release it and pumping it back underground in our territory. When we analyze all the energy resources, we can go one by one, and in the manuscript you will find fairly extensive energy cards where I summarize all these geotechnical needs. There are few lines that are common denominators for all the energy resources. We need to do proper site characterization, to get the right material properties for design, to develop proper monitoring strategies incorporated into reservoir management and disposal management, and to design the infrastructure not only to build it, but also to retrofit it. And why not to decommission it? We are in the process of decommissioning major nuclear power plants with great challenges, I may add. Furthermore, there are great needs for energy storage, as well as for the storage of energy waste, being fly ash or nuclear waste, or CO2. And of course, there are plenty of environmental related issues, and why not make our processes more efficient and conserve energy in so doing? So as we are facing such a great challenge, we have to go back to the fundamentals, like Terzaghi did in the 1920s. This is a wonderful quote. Terzaghi said, Coulomb purposely ignored the fact that soils consist of individual grains. That was very useful for a while, but in fact it became an obstacle against further progress. So we need to go back and recognize that soils are made of grains in order to advance. And I'm taking that once again today, almost 100 years later, for the second part of the presentation, which will look at the essential of soils. And we are going to see the grains, but also the counterside, which are the pores, and the components that fill the pores. That means the fluids. And then the couple of evolving engineering problems. So let's start with pore fluids. And you're going to see a sequence of nice movies and images. But once again, the important thing here is to understand the complexity of multiple processes that coexist. And the reason why fluids become particularly important in the energy sector is because there are so many of them in so many different phases. In our field, we have basically considered water and air, vapor, and to some extent the L-naples and D-naples. Now the variety is much more extensive. So let's make a brief list. We can encounter gases, not only air, but also methane and CO2. CO2 with pressure and temperature becomes supercritical, or it could liquefy. We also find water, and in many places we are looking for layers filled with brine. Oil, of course, that will range from light to heavy oil, and sometimes solids will precipitate, or liquids may form ice or hydrate. We will observe some of these as we move along. So let's start with one of the simplest properties, which is density. Look at the wide range in densities of these fluids. I'm highlighting two in particular: supercritical CO2, which will be most likely the way we're going to inject it underground, and brine. As you can see, supercritical CO2 is approximately 60% lighter. That means that it will float, and there will have to be a seal layer to hold it into place, and it will spread out like a pancake until it is somehow trapped geometrically or by capillary trapping. There is a huge range in viscosities. When we talk about hydraulic conductivity, we pay attention to water, and that is controlled by the inherent permeability, which is basically varying in more than 10 orders of magnitude due to the specific surface and the pore size. Now we have to also recognize the viscosity. And as you can see, viscosity changes also in more than 10 orders of magnitude. The combination makes this combined parameter in a huge scale. By the way, it is not clear whether the last image is running or not, because that drop will fall in the next 8 years. That is the longest running experiment. Now, when we have gas and water, and we begin pressurizing, the gas tends to dissolve in water to different extents. On the left-hand side, you saw a droplet of CO2 dissolving in water. Water has a pH indicator, and what you actually saw is that as the CO2 was dissolving in water, it was acidifying, forming carbonic acid. That is the low pH of Coca-Cola, and it was diffusing away into the soil. These are all time-lapse photography, so they are played at high speed. On the right-hand side, you saw that the CO2 is on top of the water, and as the water intakes the CO2, it becomes heavier, and it creates these tears and convective currents that will sustain the process going. This is the dissolution of gases in liquids. This is the dissolution of salt, table salt, sodium chloride in water. You see the water molecules. This is a ball model, so the two sticks to simplify the display. And water begins wedging itself and eventually hydrates the chlorine and separates it. Eventually, more water will come in and will remove the sodium, and eventually we form these hydrated ions, which is salt water. Now, if we take a droplet of salt water and we let it dry and we watch it carefully under a microscope, it gets to a point that the water cannot have more salt in solution, and salt begins reprecipitating. When there are phase transformations, the water freezes, and it will all depend on whether the water likes the mineral or not. It will actually form an ice sheet on top, or it will just remain localized at the contact. But there is one type of phase transformation which is quite exceptional. Typically, when water freezes, it excludes anything that is not water, for example, ions. However, if there is methane, the methane molecule can get locked in, trapped, surrounded by water molecules that form a cage. This is called methane hydrate. It takes relatively high pressure, let's say 600 meters beneath the ocean, and low temperature in order for this to happen. But you may be surprised to know that we find methane hydrates offshore pretty much everywhere around the world and beneath the permafrost. And there is more carbon trapped in methane than in coal, petroleum, and gas. So this could eventually become an exceptional energy resource, with a caveat that if it gets released into the atmosphere, it's a devastating greenhouse gas. Another part of the fluid-related processes that we need to recognize is that there are many of these processes that produce very pronounced volume expansion. Of course, we're all familiar with the expansion of water to form ice. That is only 9%. When we open a Coca-Cola can, it will expand probably 50%. If we take methane hydrate, the one I just showed you before, these little cages of water with methane molecules inside, it will expand 176 times, not percentage, times. And of course, the wonder of the steam engine is that when water vaporizes, it expands more than 1,000, almost 2,000 times. Let's put that into perspective. When we take a soil and we shear it and we measure the volumetric dilation, that rarely exceeds 10%. So now imagine having these fluids that will expand hundreds of times. What will it do to effective stress and then soil behavior? In fact, what you see there is a little sketch of a little methane hydrate crystal at the center that will expand when we reduce the pressure. When we sample it, it will expand this 176 times. And it will develop capillary forces that will push grains out. And what you are going to obtain with standard sampling is something that looks very much like chocolate mousse, a completely destructured sediment that is impossible to characterize. We will come back to this. Let's bring all these fluid-related processes into a couple of simple cases in the context of re-injecting CO2 underground. And so there you see a water droplet sitting on a calcite crystal surrounded by liquid CO2. The water is heavy, so it sits on top of the crystal. And if we wait, the water begins evaporating. That means diffusing, dissolving into the CO2, as you saw earlier, where it was changing the colors. But CO2 dissolves into the water, and it makes it acidic, and it begins dissolving the calcite crystal. Well, when water continues evaporating, then it cannot handle the dissolved calcite anymore, and it will reprecipitate it on the surface. Let me show you that that is indeed the case. When you look with a scanning electron microscope, you see all the reprecipitated calcite. These two processes, dissolution and precipitation, are going to be continuously occurring. In fact, they are continuously occurring in our sediments, but are going to be exacerbated in energy applications. If instead of looking at the droplet scale, we look at the whole CO2 pool reservoir, to summarize, we are going to have precipitation of salts near the injection well where dry CO2 goes in. We're going to see capillary trapping beneath the seal layer and on the boundaries holding this spreading pancake. Dissolution of the mineral where the water acidifies, and those convective currents that are going to sustain the process. And we must wonder, how long will the CO2 remain trapped? To summarize the first part of pore fluids, we can encounter them in many different phases. They have a very wide range of properties. They will trigger dissolution and precipitation exsolution processes. There will be phase transformations, and in many cases, those will be accompanied with very large volumetric changes, which will dramatically affect soil behavior. If there is anything that in our field we have made great advances, and that we are the holders of understanding that nobody else has, is in unsaturated soil behavior. And as you saw earlier, this is all going to be pretty much about mixed fluids. So my question now is, for all those of you who work in the field of unsaturated soils, how easy it is to transport our knowledge to other energy-related applications. Well, it all starts at the molecular scale. The reason why we can float a paper clip is because of the formation of this interfacial membrane that develops at the interface between two fluids with limited miscibility. On the left-hand side, in the lower part, you see water surrounded by methane molecules at low pressure. There is limited compensation of intermolecular forces, But as we increase the pressure on the right-hand side and we have a higher gas density, there is better molecular interaction, better compensation, and interfacial tension should decrease. Therefore, interfacial tension is pressure dependent. Now, the contact angle, now when we have the two fluids interacting at the mineral, on the mineral surface, the contact angle then also becomes pressure dependent. And the fluids may like the mineral, depending on their mutual preferences, or not. And typically, we always talk about capillary rise. That is when the water likes the mineral. But you could have negative rise in the case of, for example, oil or mercury. So we have to pay attention to these two parameters in understanding unsaturated soil behavior in the largest scale of energy applications. Let me demonstrate that this is indeed the case, that pressure alters these parameters. You are watching through a very thick sapphire window at the water droplet on top of Teflon. We surround it with CO2. We begin squeezing the CO2, increasing the molecular density, and you see how the water droplet changes the shape dramatically. The reason is the contact angle is changing. The CO2 likes Teflon more than the water does, and the interfacial tension is changing. This is going to happen within the reservoir. To summarize, in our field of unsaturated soil behavior, we have consistently thought of pretty much water and air. That is 72 millinewtons per meter surface tension. But actually, this can change in a wide range, and we can actually engineer it with detergent, with surfactant, and bring it down to very low values indeed. At the macro scale, there are a couple of fundamental concepts that we use extensively. One is suction, the pressure difference between the two fluids, and the net stress, which is the difference between the boundary stress that we apply and the air pressure. The other macro scale concept that captures pretty much the structure of the soil is the soil water characteristic curve that gives us an idea of how the fluid is interacting with the pore size distribution and pore size connectivity in the sediment. I will not mention much more about the entry pressure, but it's going to be a very critical parameter in many aspects of the energy cases. All these macro scale concepts, we tend to think of the two fluids being pretty much homogeneously distributed. Now, more and more, we are beginning to use these wonderful tools of micro CT to see what is exactly going on inside. Here, the grains have been made transparent, and you only are looking at the water menisci between grains, what is pretty much sketched on the right-hand side of this figure. And you see that these water menisci form interconnected patches of water, and everywhere else, there is pretty much not water. Therefore, imagine the interparticle forces with the addition of the capillary forces. This is quite a complex and inhomogeneous situation, which adds some complexity to our understanding of unsaturated soils. Precipitates would like to do so in the largest pores. So if we have hydrate formation or mineral precipitation, this will occur in the largest pores. And if we close the largest pores first, our soil water characteristic curve will be significantly affected, particularly on the right-hand side, where the entry pressure is. Now, if we begin dissociating the hydrate, the soil water characteristic curve is changing because we're removing that solid. And so we have a continuous time-dependent process, adding significant complexity to all this analysis. Another departure from what has become classical in unsaturated soils is the fact that in unsaturated soils, the air invades quite homogeneously the previously saturated medium. However, when you open a Coca-Cola bottle, you create bubbles, you nucleate bubbles everywhere. That means that when water with dissolved gas or oil with dissolved gas, what is called foamy flow, or hydrate begins dissociating, we're going to see gas developing everywhere, like you see on the lower micro model on the lower set of images here. The upper part is when there is invasion. The lower part is where it nucleates everywhere. So we have to rethink what are the implications to the soil-water characteristic curve, the Van Genuchen equations, the relative water and gas permeability, etc. Finally, in this reanalysis of unsaturated soil behavior, I would like to highlight that we tend to assume that there is thermodynamic equilibrium. That means that things have homogenized throughout because it has been the result of a slow process. In fact, many of these tests take typically 6, 8 months or 1 year to do a proper soil-water characteristic curve test. However, that is too long for the removal of petroleum or gas. So there will be no thermodynamic equilibrium, and in fact, what is going to happen is that we're going to mobilize viscous forces. And if we're injecting CO2, remember supercritical CO2 has much lower viscosity than water. Now that CO2 is going to go through the largest interconnected pores and is going to finger through, and the rest of the brine is going to remain behind. We're going to have very inefficient invasion when we inject CO2. By the way, conversely, if we were pushing a very viscous fluid against a defending fluid, a saturating fluid which is low viscosity, we are going to have a more homogeneous front. So on the lower half of this plot, we have classical unsaturated soils. On the upper part, where velocity gains relevance over capillarity, we have to begin looking at the relative balance between the fluid viscosities. Without any further demonstration, I would just like to say that it may surprise you, but the same way we talk about interfacial tension between water and air or water and oil, vinegar and oil, there is also interfacial tension between water and ice, water and hydrates. And so we can extend all these concepts to all these other materials. And for example, if the capillary forces are greater than the effective stress-related forces, and that will happen when the effective stress is low or the grains are very small, then the capillarity will prevail, and we're going to form gas-driven fractures. We are going to form ice lenses, hydrate lenses. Otherwise, when effective stress is high and capillary forces are small, the diameters are large, we are going to have a completely different invasion mechanism and pattern of solids. To summarize mixed fluids, we need to recognize the wide range of fluids that are involved and their phases. The surface tension and contact angle are not constant anymore, and in fact, they vary with pressure, and we may control them, we may engineer the system. The residual saturation that we are concerned about in unsaturated soil behaviors is what controls our ability to recover gas and oil. In fact, we leave approximately 50% of the oil in the reservoir because of residual saturation. That entry pressure that we didn't say much about is the one that is going to control how far that pancake of CO2 is going to spread out and whether the seal rock will be able to hold the pool underneath. That the soil water characteristic curve has to be reconsidered, and that there are several instabilities that may affect the process, and we need to understand them better to analyze these systems properly. That was one part of the presentation. We were looking at the fluids and the pores. Now I would like to look at the grains that make the sediments. We are going to do it in 3 stages: the genesis, to pay attention to post-formation changes, and I will highlight why, and then to look back and reconsider classification of soils. We typically talk about genesis as weathering of rocks followed by a transportation agent. Well, when we look at the whole energy sector, we run short with such descriptors. In fact, we have to look at mechanical, thermal, biological, and chemical processes in the formation of grains. Few slides to demonstrate the case. Mechanical forces are big enough when the grains are large, so the impact between grains can cause damage, or the abrasion between grains can alter their shape. Therefore, mechanical forces can only explain the formation and evolution of coarse grains and few seals, for example, beneath glaciers. Thermal processes are also very critical. This is an artificial one, a man-made, which is fly ash. And because it formed from a melt, you see the effect of surface tension in this nice spherical shape of fly ash. By the way, the fly ash had lots of gas during the formation. Some of these will be hollow, and some of these will be like xenospheres. And be careful, the specific gravity is not 2.65 anymore. It can be from 1.7 to 2.2, 2.3, which completely messes up our thinking of void ratios, etc. These materials, even when we call them non-puzzolanic fly ash, do develop some early diagenesis, let's say within a week. And they increase their stiffness significantly and may lock porosity because they will not consolidate so nicely. Some of the consequences are, for example, seen here in the failure of the TVA Kingston storage, almost 6 years ago now, 5 years ago. The natural example of that is volcanic ash. The same happens when molten lava explodes and comes out. And typically, we don't see this, but you also see the surface tension here in the shape. Most likely, it came out with so much gas that those bubbles actually exploded, and you see like the shreds, the shells, the pieces, and the concave shapes left by the gas. This is, for example, the formation of Mexico City soils. By the way, the volcano is called Popocatépetl. That's to practice the language there. And those ashes fell on a lake, and water-mediated processes of dissolution and reprecipitation form what is Mexico City soils today. However, how can we explain that the soil with a liquid limit that can reach 400 can exhibit a friction angle that can exceed 42, 44, 46 degrees? Well, we need to look at the other genesis, which is biogenesis. There was lots of bioactivity in the lake, and that led to the formation of diatoms. And whenever we encounter diatoms in our soils, being here the Cooper Marl or Ariake clays or Mexico City clays, we always see exceptional combinations of liquid limit and friction angle that we cannot explain otherwise. When we go offshore, and here I'm showing an example from the Uljum Basin between South Korea and Japan, we encounter complete layers. You still see some diatom here, but everything else here is crushed diatom. Very small pores, huge porosities, behavior that is non-plastic, yet very high liquid limits. Precipitation of salt is the mechanism that leads to the water-mediated formation of clays. These are all, in most cases, precipitates as well. And in fact, you see the importance of the crystallographic structure prevailing and the formation of these classical shapes, leading to kaolinites, ilites, smectites. So we saw that there are different formation mechanisms leading to different particle shapes, different sizes, and different mineralogies. Let's explore the consequences of size. When we analyze all the forces acting on particles, and those are the forces that cause motion of particles, there wouldn't be strain, there wouldn't be shear without unbalanced forces at the particle level, then we realize that these forces all depend on particle size, either linearly, quadratically, or cubically. Just for the sake of this presentation, let me explore some of the balance between a couple of these forces. On the lower part of this plot, you see the balance between the effective stress-induced force on grains of different size, when the effective stress is just nominal, 10 centimeters of soil, 1 kilopascal. And you also see the capillary force that you can mobilize between grains due to that water menisci that forms between grains. To the left-hand side of this intersection point, capillary forces are greater than that very small effective stress. That means that capillary forces will prevail in small grains. In large grains, capillary forces are smaller than either the weight of a particle or effective stress, and therefore you cannot make sand castles with large grains. In order to explore the effect of electrical forces, I really have to look into strains because it's more difficult to analyze their balance. And so when we do that, we compute the strains that a soil will exhibit by changing deionized water for brine. That will alter the double layers, the van der Waals attractions, etc., and that will cause a strain, and that strain will be basically zero until we reach the submicron particles. Therefore, there are two very important ranges here where the physics changes. For small particles, we have to begin paying attention to capillary and electrical forces. Summary. We have already seen the relationship between genesis, size, shape, and forces. And what is very interesting here is that that is where the sieve 200 is. The sieve 200 is an exceptional choice. It's more than just a convenient choice for laboratory purposes. It's an exceptional choice from a physical point of view. Furthermore, in order to better understand the fine grains, we have to pay close attention to the fluids. In the coarse grains, we need to add a little more information. Particularly, we have to emphasize particle shape, not only size and uniformity. So we saw that there are different geneses, the importance and implications of genesis, and the relevance of the sieve 200. Most of our engineering projects have been for, let's say, one generation. Somehow we have decided that the next generation has to build its own infrastructure with the latest technology, and so we do like to take a 25, 30-year horizon in our designs. However, when we look into the energy, in many energy applications, we would like the CO2 to remain down there for tens of thousands of years, and nuclear waste probably for 100,000 years. So our time scales now are competing with the time scales of geological processes. Remember, fly ash is changing in 1 week, and Mexico City soils and Colombian volcanic ash soils form in less than 10,000 years. And now we're beginning to think of engineering projects for longer time scales. So we cannot think of soils as being inert anymore, and we have to go back and look at dissolution and precipitation. But this time I'm going to do it from the scale of the soil to see what are some of the implications. This figure shows the balance between all the processes, the diffusions and the advection and the reaction. And what is important here, in the upper part, the water is moving very slowly and the reaction is very fast. So as water advances, all the reaction is taking place. And the dissolution is a homogeneous front moving along. On the lower part, the water is moving quite fast relative to the rate of reaction, and therefore reactants will further invade into the sediment. Now let's follow the logic. The water invades and dissolves grains. Where it dissolves grains, the pore increases. The pore increases, there is more water flow. There is more water flow, there is more dissolution, and there is a positive feedback mechanism that creates the formation of dissolution pipes. So under certain regimes, we have to be very careful, and that could happen in dams, and we have seen many of those cases, and that can happen naturally with acidic rainwater, which naturally acidifies, go through the organic matter and the atmosphere as well. What happens in that case? Well, let's see an experiment to see if this is true. This is calcareous sand from here, from the Savannah River site, across the river from Georgia, and we permeate this sand with acidified water. After some time, we take the specimen. This is in an odometer, and we create a very homogeneous flow field. Instead of dismantling the specimen, we actually put it in a tomographer, and we take multiple slices, and we see all these fingers of dissolution, where some of the minerals have been preferentially eroded while the quartz remains. And now we would like to understand the implications of this localized dissolution. So we take discrete elements. We also make an odometer with all the yellow grains. However, in certain preferential columns, some of the grains, we're going to let them dissolve. Then we see how the forces evolve, and all of a sudden you see that the following force pattern develops. Where there is no dissolution, the grains have to carry most of the vertical load. However, in the columns that dissolve, now the grains are not picking up the vertical load, but they are laterally holding the columns so they don't buckle. And in those dissolved areas, there has been a 90-degree rotation of the principal stresses in the same soil mass. The consequences can be quite scary. So in the last 2 or 3 years, while they were building two of the very few new nuclear power plants being built in this country, here in Savannah, near Augusta, the Georgia Power, or the Southern Company, decided to actually excavate the upper 120 feet to make sure that they would go below the layer that was experiencing localized dissolution. An expensive proposition, but it was key to avoiding the risks involved. Remember that when dissolution is very fast compared to the rate of advection, you have homogeneous dissolution. So let's simulate that in the laboratory once again. This is once again in an odometer cell, but it allows us to measure K0. This is at the beginning, before dissolution. K0 is about 0.6 in this case. And then we start dissolving and see what happens to K0. K0 goes down, it reaches 0.3, and then if we continue dissolving, K0 increases once again. Now, this low value is Rankine's active earth pressure coefficient. Let me translate that. The soil reached failure under zero lateral strain conditions. We always fail the soil in a triaxial. No, this is in an odometer when the soil is experiencing dissolution. And so once again, let's go back to discrete elements to see what happens when we do that. And now we're dissolving grains, and you see that in certain areas, the forces are homogenizing. However, in some bands, the forces are becoming very strong, and in fact, those are shear bands. So not only that the soil fails, but under certain conditions, it may experience shear banding under zero lateral strain. And if you think that this is a numerical artifact, let me show you field evidence from all over the world. We encounter these polygonal faults at the bottom of the ocean that cannot be explained with Terzaghi's consolidation theory. And we see that the bottom of the ocean has these lines. These are faults. If you magnify one of these from green arrow to green arrow, you see that discontinuities between layers. And in fact, when you expand this one-to-one scale, you see that they are all at 45 plus phi over 2. There is no extensional mechanism. There is no tectonics. And the bottom of the ocean, contrary to what you think of Terzaghi effective stress consolidation theory, is massively sheared, with tremendous implications to intercommunication between layers and what we call the geoplumbing. We've been playing with points and counterpoints. The counterpoint to dissolution is precipitation. If you explore the different forms of precipitation, we begin identifying few common trends. One is that it may precipitate at contacts, like the formation of loess, typically will reflect unsaturated soils where menisci form. Two, it can cause surface coating. We saw that in ice. It could be homogeneous nucleation in the middle of nowhere in the pore. That is very unlikely. Most likely will be heterogeneous nucleation, where it will nucleate on the mineral surface and grow into the pore. And if you wait long enough, there is something called ripening, where all those minerals tend to come together and form these patches of cementation. And as we showed earlier, if the forces that these cements develop are strong enough, they may separate grains apart and form lenses. We see that with pyrite, we see that with hydrate and many other, gypsum, etc. These are, once again, analogs found in nature for different formations. What is the immediate consequence of precipitation? The most relevant one and the most detectable one is the increase in shear stiffness. On the left-hand side, you see the change in shear wave velocity. You see the arrival time of shear waves. As we increase the effective stress, the travel time gets shorter, the shear stiffness gets higher. Then the lower part, the stress decreases, and the travel time increases. That is an uncemented soil. On the right-hand side, you see exactly the same sand with minute cementation. The shear stiffness, the travel time is very short, the shear stiffness is very high, and the velocity is constant, stress independent, because now stiffness is cementation controlled. Now, how effective the cement will be will depend on the pore habit, what we described before. How did it like to precipitate? And for example, here you see the effect when it precipitates everywhere, a little bit in every pore, or in patches. And it affects the stiffness, the strength, the angle of dilation, the critical state parameters. So pore habit will have an effect as we try to anticipate the evolution of the physical properties of our sediments. Post-formation changes are critical as we begin looking into long-term projects in the energy sector, where the time scales are going to be long. Therefore, as Jim Mitchell reminded us many times in the past, we must change our attitude. Soils are not inert. Dissolution and precipitation processes are probably some of the most important ones that we should consider. And underneath all these, I was talking about coupled hydrochemomechanical processes. We have spoken so much about sediments that I think there is a good opportunity to reconsider one of those basic concepts in our field, which is that of soil classification. The unified soil classification is the basis for soil classification all around the world, and it is indeed exceptional. Look at the first decision that we make. We use the sieve 200, and we showed earlier what an exceptional choice, physically robust, the choice of the sieve 200 is. Then we keep going, and if we ask whether there are enough fines to fill pores and affect behavior, if there are not enough fines, then what is important is how well the grains will pack. And so for the clean sands and the clean gravels, we will ask about the coefficient of uniformity. By the way, we should also ask about particle shape, which is as important as coefficient of uniformity in the development of Emax and Emin, in other words, the packing of grains. On the lower part of this plot, look at the first decision that we make. What is the liquid limit? And the importance of the liquid limit is because it tells us really how much specific surface there is in that sediment. Then we proceed, but at this point, I begin to have a few questions. We make choices and we choose 50% passing or 50% retain for gravels, for sands, for cores, and fines. And one has to wonder whether this is true soil behavior, or I don't know, a prevailing democratic principle post-war in the 1940s. Then we have to go back and look at the classification of fines. So let's explore some of these briefly. If we do some gravimetric volumetric analysis, and we see how much sand we need to fill the voids in a gravel, we can identify two boundaries here. One in which the gravel is densely packed and the sand is loosely packed. That will be the minimum amount of sand that we need. Or the other case in which the gravel is loosely packed and the sand is densest. That will be the maximum amount of sand that we need for that transition. This Emax and Emin, as I just said, depends on coefficient of uniformity and particle shape, but in general, it appears to be somewhere between 20 and 40%. It is not 50. Soils are not democratic. Now you may wonder about how we do this analysis for fines. Well, in the case of fines, we cannot talk about Emax and Emin for the clays, so we are going to pack the clays something close to the liquid limit. Let's say at an effective stress of 1 kPa for the lower bound. And we're going to say that the clay is picking up all the load, and we're going to take a nominal load of 1 megapascal for the upper bound. When we do that, and we take into consideration all these correlations between void ratios and coefficient of compression coefficient as a function of liquid limit, we conclude that the boundaries are somewhere between 8%. You already fill all the voids with montmorillonite. You have plugged all the porosity. Your hydraulic conductivity has dropped by 10 orders of magnitude. And that you actually pick up all the load somewhere when you have 25%. And at that point, because the compression lines converge at higher stress for the different clays, it really doesn't make much of a difference whether you have a high or a low plasticity clay. 25% is our number there. Let's go back to Savannah River. This is Savannah River data, and the liquid limit here is on the passing sieve 200. It is very important that probably we reconsider our choice of running the liquid limit on the passing sieve 4, because those coarse components have a huge effect biasing the validity of the meaningfulness of the liquid limit. So here I'm showing the liquid limit passing sieve 200 versus the fine fraction, and 50% would be the boundary that the unified soil classification tells us. So for all practical purposes, these are indeed sands with clays. However, they are above the upper limit. That means that without any doubts, the clays are picking up all the load. So the clays are controlling hydraulic conductivity, are controlling stiffness, and are controlling strength, and it is indeed a misnomer to call the soil a sand. So as we move further, we ought to think, how are we going to reanalyze soil classification so that the labels that we assign to our soils are meaningful from the point of view of behavior and understanding? So in order to go further, let's reconsider the lower part of the soil classification, which is the classification of fines. And this is Casagrande's 1948 chart. That is the A line. And notice what falls underneath the A line. Organic material. But there are also a couple of clays, a couple of kaolinites. However, we call those silts. And now we have to think, what is the meaning of a clay? Is a clay size, clay mineral, a material that is above the A line? There are multiple semantics for clays and often confuse us. When we look at the expanded version, now we really grasp the purpose of this chart. You see, there are two big blocks that Casagrande separated, the diatoms and the organic matter, which are like diatoms. Imagine a piece of wood, it has lots of voids inside, yet many pieces of wood behave like a sand, yet they would give you a very high liquid limit. So that is what they were really trying to separate, apparently. This is data, more than 500 soils here, and that is the best fit. Look at the very strong correlation between plasticity index and the liquid limit. You may wonder, why does it intersect at 30%? Well, that is the amount of water that a sand or a silt will have near Emax. So at that point, a non-plastic material goes from being a solid to a liquid with zero transition, plasticity index equals 0, liquid limit equals 30. That is the intercept. The second one, we have to wonder, how come there is such a strong correlation? Well, the reason is, this is the plot of the plastic limit versus the liquid limit. The plastic limit is very small. So basically, we're plotting liquid limit versus liquid limit. And that is the A line. And then what were they trying to do? They were trying to make sure that the liquid limit was not the liquid limit of a clay. It was they were trying to pick up the presence of diatoms and organic matter. From an energy point of view, probably trying to pick up when are soils becoming electrically sensitive may be a more important decision to make as we move forward. Summary, let me suggest, this is just a suggestion at this point, how should we probably enhance our unified soil classification? We should change those 50-50 percentages for the definition of coarse and fine, and for the mixtures of sands and gravels. And probably we ought to be thinking of calling something like the Dean norm does, some transitional soils in between. For the fines, what is important is indeed the liquid limit. But in order to make sure that we don't have at high liquid limit a diatom versus a montmorillonite, we ought to be looking at the electrical sensitivity, and it could be as simple as running liquid limits with deionized water and with brine. Now, the concept of clay changes once again, and we're going to call clay those soils that are electrically sensitive, which is probably a meaningful definition in the thinking of all the possible fluids that will affect our applications. I would like to finalize this section on sediments by saying that the unified soil classification indeed has great physical insight. It's amazing the great intuition and more than intuition, great physical understanding we had a century ago. However, we have gained much knowledge since, and probably we ought to consider updating the unified soil classification so it becomes more meaningful. The labels and the behavior bring together a better relationship. And we need to add a little more information on the course, the shape, on the fines, the fluids. The next section is very short, and I'm just going to tie together a few things that we have already said and raise awareness of some challenging problems that are evolving related to the energy applications. Remember that sketch? That was the large volume expansion the hydrate experiences when we depressurize it. Borslev wrote an amazing manual in 1949 for soil sampling, but they didn't face the problem of gassy flow or very expansive conditions that we face in many of these applications where we start with high pressures. So how are we going to conduct sampling and testing when the material that we get out literally looks like chocolate mousse? Let me show you what is developing nowadays. This is the idea. We go to the middle of the ocean and we push down something that looks like a piston sampler but has a big ball valve at the bottom. And so after we core or we push the sampler, we start retrieving it and we close the ball valve and we lock in the pressure. We bring it all the way to the surface with the full pressure, 20, 30 megapascals inside. So while the sediment may have experienced the de-stressing and all the sampling effects of changing effective stress, at least still has the fluid pressure, the dissolved gas, the hydrate, without dissociation. Once it is at the top, it is in an autoclave that is presented here, the core being in orange, and we connect it to a series of tools. We couple them, we build the pressure on the left-hand side, we equalize pressures, we open the bridge, and now we go and grab, with a telescopic arm, we grab the core. We bring it back in, we depressurize, close the ball valve, depressurize the bridge, disconnect the autoclave, and now we have it here waiting for the tools to come in. Remember, I want to cut the core, I want to run a triaxial test, a direct shear test, an odometer test, a flexible wall permeameter, without ever removing 20 or 30 megapascals, 2 or 3 kilometers of water of pressure. And so the next step is we bring the tools, we connect them, we build the pressure, we equalize the pressure, we connect, and now we transfer the sediments into the tools where the different measurements will take place. Here are indeed, it has been built, and here are some examples. That is a hex saw. That is the same hex saw that you have in your machine shop, but it's working internally at 30 megapascals. And this is a direct shear box a double ring direct shear box. And this is an odometer, which allows us to apply the effective stress back again without ever depressurizing the pressure. And it has a flexible wall permeameter if we so desire. And it produces exceptional data for sediments that could otherwise not be tested in any meaningful way. The next topic that is going to be critical is that this long duration infrastructure and facilities and systems are going to experience a large number of load applications. And these loads could be thermal cycles, could be relative humidity cycles, like in compressed air storage in caverns, or once again, thermal cycles here showing energy piles, or effective stress cycles, like the foundations of wind turbines. And that brings us back to Leonardo, who conceived the idea of the ratchet, where there is a displacement and a locking mechanism, in our case, friction. And so every time we displace, then it gets locked in by friction, then we displace more, and the system may begin crawling, and it may have significant impact in long-term performance. Let me give you a little insight from a physical point of view of soils. This is tau sigma QP plot on the upper part, on the lower part, void ratio versus P. On the left-hand side, the deviatoric strain. So we are going to load monotonically. That is what we always do, the green line. And so we produce, in this case, contraction, and et cetera, et cetera. And then we're going to begin cycling the load. That is the cyclic load. If we see what happens with volume, there is additional volumetric contraction that takes place, but that volumetric contraction cannot go forever. So it will reach some terminal density. And this is not the critical state. This is not the odometer stress, void ratio. This is a new terminal density that is intimately related to the process that we are imposing on the system. From the point of view of the deviatoric load, now it may be that the accumulation of deviatoric strains arrest and the system reaches what is called shakedown. But they may continue going forever. And in fact, if you look at that geomembrane, during the cooling and heating cycles day and night, it began wrinkling because of thermal ratcheting continuously going down, with all the implications that Kerry Rowe has told us about those wrinkles. Now, the analytical models, the algorithms, the experimental devices to confront these new type of loads are in their infancy, and we really need to devote much attention to them. Just a simple example here underneath the wind turbine. At the beginning was the result of the static loading, and now the 100,000 cycles are being simulated, and you see the gradual accumulation of vertical deformation and changes in void ratio that may indeed affect the long-term performance of this foundation. And finally, throughout this presentation, I have given you several examples where things are not homogeneous, as Coulomb said. In fact, where there is not only spatial variability in the materials, but actually the process themselves cause spatial variability. Remember the dissolution and the shear bands, the tears and convective currents with gas dissolution, the formation of gas-driven fractures, dissolution pipes. I didn't mention this one, but this is clogging during fines migration when we produce oil, or ice lenses when we freeze soils. We have spent the last 40 years talking about shear bands. There are many other instabilities that will affect our interpretation and our analysis of our systems. Summary of these engineering developments: sampling and characterization is amazing what Borzlov told us. We have significantly great challenges facing us. This is all us. This is our field. Repetitive loads will affect the long term. They can come in many different ways, and we are just at the beginning of developing proper models, algorithms that do not lead to accumulation of numerical errors, devices and test protocols to actually measure constitutive parameters. And now I'm extending what I said earlier. We have hydro, thermo, chemo, bio, mechanical coupled processes, and some of those couplings lead to the emergence of confusing instabilities. Closing thoughts. I hope I was able to convince you that energy is indeed critical to life, and that the energy challenge is huge because we need to increase access to energy by 50% in the next 25 years. There is a beautiful synergism here between our field and the energy field. For us, the energy stimulates us to gain new insights into soil behavior. For the energy field, we are critical. We are at the core to the development of a sustainable energy solution for the world. Every time we've been challenged, we have gone back to our foundations. Terzaghi did it, the earthquakes did it for us, environmental contamination, now again, in the energy sector. And I think that we ought to welcome this. It's an opportunity, an incredible opportunity to re-energize our field. Look, on the left-hand side, you see the table of contents of our typical courses. And we see that the energy geotechnology is nothing new. It's just extending what we know and making sure that we recognize that there are much higher effective stresses, much higher, wider range of temperatures, wider range of fluids, and the long-term duration of these projects. For the younger members in the audience, for those in their earlier careers, I think that you are going to be at the prime of your careers, confronting this unprecedented global challenge. For those in practice, there is indeed an infinite number of great engineering problems out there, and let me add that it comes with great resources. For those in education, I think it's time that we prune many of those obsolete and confusing semantics and misnomers that we have in our field, that we renew our emphasis on the basics, and that we extend our curriculum to cover all the aspects that we need. And for those in research, it is indeed just fascinating. In all cases, I think that this is a time of exciting challenges, opportunities, all that with a spice of some sense of urgency. I'm very grateful to many individuals and organizations, and to all of you for listening. Thank you.